Welcome to this lecture on parasitology. Today, we are going to explore a fascinating but devastating microscopic parasite known as Pratylenchus, commonly called the Lesion Nematode. If you have ever wondered why seemingly healthy crops suddenly wither and die despite getting enough water and sunlight, the answer often lies hidden underground. By the end of this session, you will understand not just the biology of this hidden enemy, but also how agricultural scientists use mathematics to predict and manage the massive damage it causes to our global food supply. Let us start by picturing a beautiful, healthy garden. Suddenly, your plants start wilting and turning yellow. You water them and add fertilizer, but nothing works. Why? Because the enemy is invisible and underground. Pratylenchus nematodes are microscopic worms that act like tiny bulldozers. They tunnel directly into the roots of your plants. As they crawl through the root tissue, they crush the plant cells, eat the contents, and leave behind a trail of dead, rotting tissue, which we call a lesion. Since roots are the plant's drinking straws for water and nutrients, these microscopic bulldozers effectively starve the plant to death from the bottom up. Now that we have an intuitive picture, let us look at the formal scientific definition. In parasitology, Pratylenchus is defined as a genus of microscopic, unsegmented roundworms. Specifically, they are classified as migratory endoparasitic nematodes. These two words are very important. The term migratory means that, unlike some parasites that attach to one single spot and stay there forever, these nematodes constantly move around. They migrate both inside the plant root and out in the surrounding soil. The term endoparasitic indicates that they physically enter and live inside the host's internal tissues to feed and reproduce, rather than just attaching to the outside. Understanding their classification leads us to how they actually feed. These nematodes possess a highly specialized needle-like mouthpart called a stylet. You can think of it as a microscopic hypodermic needle. They use this stylet to physically puncture the tough plant cell walls. Once inside, they inject digestive enzymes that liquefy the cellular contents, which they then suck out. Because they are migratory, they do not just do this once. This continuous cycle of puncturing, feeding, and moving causes extensive localized cell death. This widespread cellular destruction is exactly what results in the characteristic dark necrotic lesions on the surface of the root. To truly grasp the damage we just discussed, let us look at this cross-sectional diagram of an infected root. Notice the rectangular green structures. These are the healthy plant cells. Right in the middle, you can see the nematode tunneling through the tissue. Look closely at the front of the nematode. That sharp protrusion is the stylet, actively puncturing a healthy plant cell to feed. Now, look behind the nematode. You will see a trail of dark, brown, decaying cells. This is the necrotic lesion we talked about. The diagram perfectly captures the destructive path of this migratory endoparasite as it moves through the root, leaving a wake of dead tissue behind it. Seeing the physical damage at a microscopic level helps us understand why this parasite is such a massive global threat. Pratylenchus is absolutely critical to study because it ranks among the top 3 most economically damaging plant parasitic nematodes in the entire world. They do not just attack one type of plant. They infect a massive variety of essential crops that we rely on daily, including wheat, corn, coffee, bananas, and potatoes. Because they are so widespread and destructive, they cause billions of dollars in agricultural losses every single year. If left unmanaged, these microscopic worms pose a severe and direct threat to global food security. The economic damage is not just from the nematodes eating the roots. The physical wounds they create act as open doors for other deadly soil-borne pathogens. When the root is torn open by the nematode's stylet, destructive fungi and bacteria in the soil can easily enter the plant. This combination leads to complex disease syndromes, where the plant is fighting multiple infections at once, making it almost impossible to survive. This is why agricultural scientists must understand the biology of these lesion nematodes. If we cannot control the initial nematode infection, we cannot stop the secondary fungal and bacterial infections that follow. Because the threat is so severe, we cannot just wait for the plants to die. We must be proactive. To manage these parasites, agricultural scientists use mathematical models to predict exactly how much damage a specific population of Pratylenchus will cause to a crop. These models are vital because they help farmers decide if the number of nematodes in the soil is high enough to justify the high cost of applying chemical treatments. By calculating the expected loss mathematically, farmers can make economically sound decisions about crop management before they even plant the seeds. Let us look at the most fundamental model used for this. This brings us to the linear yield loss model. Conceptually, this formula starts with the perfect scenario, a maximum yield, and subtracts the damage caused by the nematodes present in the soil. The formula is y equals y max minus c times pi. Here, y represents the actual crop yield the farmer will harvest, measured in kilograms per hectare. Y max stands for the maximum possible yield if there were absolutely zero nematodes in the soil. Pi represents the initial population density of Pratylenchus in the soil before planting. Finally, the constant c is the damage coefficient, telling us how much yield is lost for every single nematode. Notice that as the initial population pi increases, the subtracted term becomes larger, meaning the final crop yield y will decrease significantly. Let us apply this formula with a concrete example. A farmer is preparing to plant wheat. Laboratory tests show an initial population density of 500 nematodes per 100 cubic centimeters of soil. The maximum possible yield for this wheat is 4,000 kilograms per hectare, and the damage coefficient is 2. We want to find the actual expected yield. We start with our linear yield loss formula. We substitute y max with 4,000, c with 2, and pi with 500. Following the order of operations, we first multiply 2 by 500, which gives us 1,000. This means the nematodes will destroy exactly 1,000 kilograms of wheat. Subtracting this from 4,000 gives us our final answer of 3,000 kilograms per hectare. Physically, this means the farmer is losing a full quarter of their potential harvest, indicating that soil treatment is strongly needed. Now that we have seen how much damage these nematodes can cause, how do we fight back? One highly effective strategy is planting resistant crop varieties. But how do we know if a new plant variety is actually resistant? Parasitologists test this by inoculating soil with a known number of nematodes, growing the plant, and then counting the nematodes again at the end of the season. By comparing the final population to the initial population, scientists can determine if the plant provided a good food source, allowing the parasite to multiply, or if the plant actively suppressed the parasite. To quantify this, we use another important mathematical metric. This metric is called the reproduction factor. Conceptually, it is simply a measure of biological success, how many times the population multiplied over the growing season. The formula is RF equals PF divided by PI. Here, RF stands for the reproduction factor. It has no units because it is a pure ratio. PF represents the final nematode population at the end of the season, and PI represents the initial nematode population at the very beginning. The interpretation is straightforward. If RF is greater than 1, the population grew, meaning the plant is susceptible and a good food source. If RF is less than 1, the population shrank, meaning the plant is resistant and actively suppresses the parasite. Let us see this formula in action. A parasitologist is testing a new variety of coffee plant. She starts with an initial population of 200 nematodes. After the growing season, she extracts the roots and counts a final population of 1,500 nematodes. We need to calculate the reproduction factor to determine if the plant is resistant. We use our formula RF equals PF divided by PI. We substitute the final population of 1,500 in the numerator and the initial population of 200 in the denominator. Dividing 1,500 by 200 gives us a final answer of 7.5. Because 7.5 is significantly greater than 1, it physically means the nematode population multiplied by 7.5 times. Therefore, this coffee plant is highly susceptible and would be a terrible choice for infested soils. We have covered a lot of ground today, so let us review the most important ideas. First, we learned that Pratylenchus, the lesion nematode, is a highly destructive migratory endoparasite that wreaks havoc on global agriculture. Second, we saw how it uses its needle-like stylet to puncture cells, creating necrotic lesions that starve the plant and invite secondary infections. Finally, we explored how mathematical models, specifically the yield loss equation and the reproduction factor, allow scientists to predict damage and test crop resistance. By connecting microscopic biology to mathematical modeling, we can implement effective control strategies and protect our global food supply. Thank you for joining this lecture.